this point, we start discussing magnetism. We finished with electricity, right, at this point. And okay, slightly not so good, not completely good, but for half a week, recitation classes are going to be slightly ahead of the lecture because we haven't started discussing magnetism in the lectures. We just finished RC circuits, and the next lecture is only on Tuesday, right? So I will first kind of review of tomorrow's material, right? And then we will start discussing solving problems. But again, today's material, is not that complicated, so it should be fine, right? It should be fine if we're slightly ahead of the lecture class. So what is so let's assume that you have point charge, I don't know, electron, proton, whatever, right? And we know from the past that it produces electric field, right? And does it matter if it moves or stationary? It doesn't, right? If electron, for example, stationary, it produces electric field, or if it moves, flies, it still produces the electric field. But people notice that if point charge, if charge travels, there are some interesting additional phenomena which couldn't be explained by the presence of the electric field. So in order to explain them, they introduced the secondary field, right? So additional field, the magnetic field, right? So the point is the magnetic field is produced or can be produced only by a moving charge. If a charge stationary, it cannot produce magnetic field, point, the period, right? So it's just observations. God created nature this way, right? So only if a charge moves, there will be magnetic field around that. But electric field, it doesn't matter. Charge stationary, charge moves, electric field will be everywhere. But in order to produce magnetic field, charge must move. So that's the basic system which produces a magnetic field, a moving charge. And that's what I wrote, prepared. A moving charge creates the magnetic field. That's the basic system. And then, of course, we can come up with three systems. Right? Of course, the first one is a moving charge. Then, if you have a bunch of charges traveling in the same direction, what is that? It is a current. It is a current. So as a result, current in the wire also capable of producing a magnetic field around itself, right? And then, of course, the permanent magnet, right? So, which we use most of the time. Actually, I have here a bunch of permanent magnets, but they're very small, fridge magnets, right? Okay, so now, so these systems we're going to discuss. Right? Now, the next question: how can we detect magnetic field? Right? Very important question. You remember we addressed that question when we discussed electricity, right? Right? You remember we introduced a probe charge, right? Right. Charge, which was our probe system, right? Which is positive, small. You remember those restrictions. Now we need to apply a similar here. So how can we detect magnetic field? Obviously, that must be some system which responds on the presence of the magnetic field. And which system responds on the presence of the magnetic field? For example, we can use permanent magnet because that's the easiest system to get, right? And of course that system must be small, right? So that you would not destroy the magnetic field of which you want to measure or detect, right? So for example, it can be just compass needle. It's small. It is a magnet. It responds on the presence of the magnetic field. So we can use a compass needle as our probe system to detect the magnetic field. So as a result, I can write, so how can we detect it? Which way I wrote, a compass needle, right, can be used. That's our probe system. Compass needle is our probe system. Right. Okay, let me draw, of course, this compass needle. Maybe I will draw it here. All right. So let's say that's my compass needle. And of course, we'll know, right? We will discuss it in the lecture. Of course, the compass needle has, any permanent magnet has the south pole and north pole, right? We will discuss that tomorrow, right? Let's assume that this is our north pole and this is the south pole of a compass needle. So, according to the convention, which we're going to introduce tomorrow, the North Pole shows us a direction of the magnetic field. So, magnetic field, this. So if you put a compass needle somewhere to detect magnetic field, you see, okay, North Pole shows this way. Okay, that's the direction of the magnetic field. North Pole shows that direction, okay, that's the direction of the magnetic field. Shows that way, okay, that's the direction of the magnetic field. So probe system. Then, okay, so next, magnetic field is invisible, right, like electric field. So it's a good idea to introduce some lines which can be used to visualize the magnetic field. Very, very similar to the ideas which we used to visualize electric field, right? Some kind of lines. Let me, for example, let's take a permanent magnet. Very often we're going to use permanent magnet to discuss some stuff conceptually. Right? So let's assume that I have here a permanent magnet. No, let me make it thicker. You will see in a second why. Right. Let's say this pole is the north one, and this is the south pole of the permanent magnet. Again, every time we will talk tomorrow about this. They have two poles, south and north. And so let's say you want to map magnetic field. Of course, we know that this permanent magnet creates the magnetic field. So how can we map? Permanent, compass needle, position compass needle here, it gives us direction of the magnetic field. Compass needle here, it gives us direction of the magnetic field. I forgot to take from the stockroom of the physics department compass needles, although those compass needles are so small that I doubt that you would be able to see them, right? And I don't have a bigger compass in my apartment, right? So as a result, I have to use some marker, right? All right, so position here, you can again get the direction of the magnetic field, right? Here, here, right? And so then connect them and then create the next magnetic field line, here magnetic field line. So it's quite doable. Of course, it's tedious. It's ridiculously tedious, but you can easily do it, right? And as a result, let's say you will come up with these magnetic field lines. They will look like this. All right, so maybe here. Then also here I can draw a few. Right. And it looks like the magnetic field lines start at the North Pole and goes to the South Pole. It looks like. I emphasize on these words. Why I keep saying this, it looks like? Because any magnetic field line form closed loop all the time. It's a consequence of the fact that there are no magnetic monopoles, right? So every time any magnetic field line must form a closed loop. Here, they closed all these lines, they closed themselves inside of the magnet. So over here, that's why I make that thicker, because I knew, okay, I would have to fit a bunch of dash lines inside of the permanent magnet. So this line gets closed over here. This line gets closed over there. This also closed. This is closed, right? So all those magnetic field lines are closed lines, closed loops, right? If you manage to find a magnetic field line which is not closed, it's either you are wrong or you deserve the Nobel Prize. it means that you found magnetic monopole, right? But most likely, although it's still Nobel Prize is possible. All right. So that's why I told you it looks like magnetic field lines start at the North Pole and end at the South Pole, right? Sort of like this is plus in the electric world, and this is minus. You remember, electric field lines start on pluses and end on minuses, negative charge, right? So in here the same, right? Lots of similarities. Sort of North Pole is sort of like a positive charge, and South Pole is like a negative charge. Again, like not. So then, how can we find direction of the magnetic field, for example, at this point or that point, right? So, like in the electricity, magnetic field is tangent. Magnetic field is tangent to the magnetic field lines, right? Or I can position, for example, the compass needle, right? So, compass needle, right? So, it will look like this. So, this is compass needle. Of course, this will be the North Pole, this is South Pole, and magnetic field is tangent. Over here I can also draw magnetic field is tangent to the magnetic field line. Again, direction is given by the direction of the magnetic field lines, or if you use compass needle, of course, the North Pole of the compass needle gives you direction of the magnetic field, right? Or here I can also draw, so B. Then, magnetic field strength, exactly the same like in the electricity, right? Density of lines larger, magnetic field is stronger. Density of magnetic field lines is smaller, magnetic field is weaker. Exactly the same ideas. Lots of, okay, not exactly, but very, very similar, right? So magnetic field strength is in the density of lines. So you can quickly just look, okay, I can say that there magnetic field is stronger, there it's weaker. Okay. Now I saw the question, right? So, of course, observation that opposite poles attract, right, each other, right? So, as a result, of course, the North Pole of the needle all the time will point towards the South Pole, right? Because again, opposite poles attract, like poles repel, right? So North Pole will be repelled from this North Pole of the permanent magnet, and of course North Pole will be attracted to the South Pole of that permanent magnet, right? Yeah, of course. I just saw the question. So where was I? Right. Yeah, in density of lines. Right, and I will sort of go tomorrow in the lecture again over that, maybe slightly faster than I usually go. All right. So then, okay. Let me check if I. North-seeking pole, right? We will talk about that, right? Opposite poles attract, like poles repel, right? So I don't use that terminology, north-seeking pole, right? And I don't remember what exactly a book means by that. Right? But I think I know, right? We will discuss it tomorrow in the lecture. But I think it's the idea just this north. Okay, tomorrow, because I don't want to get into that example with the Earth. It will take me like 10-15 minutes to finish that. Right. So that's enough for today in order to deal with problems. Now, so we introduced some basic ideas, and now, of course, at this point, we need to start introducing expressions which can be used to find magnetic fields. For many years, I used what book does. It introduces expression which can be used to find magnetic field produced by the charge. But its book oversimplifies that. and a magnetic field produced by the charge is significant. That process is significantly more complicated. And our theoreticians in the department, they all the time are against. It's wrong. We shouldn't be doing this, right? Eventually, I sort of caved and I stopped discussing this equation. Although that formula, although book describes that, but it shouldn't be there. As a result, we're not going to describe mathematically this system. We're going to use it, right, conceptually and so on, right? So because that process is significantly more complicated. Then permanent magnet, description of the permanent magnet, again, it's too complicated. Of course, we're going to use it to discuss some conceptually some questions, right? But again, mathematical description of that is outside of the scope of this course. Most of the time, we're going to discuss magnetic field produced by currents, right? So that will be our major system, right? Okay, so as a result, let's write down the expression which can be used to calculate magnetic field produced by a current. And this expression is basically a fundamental expression. It cannot be derived, right? Bunch of experimental results. You hire a graduate student, right? And he will come up with something which would fit that data, right? So we just present, it's like a Coulomb's law, like Gauss's law. This is something fundamental, right? It's called the Biot-Savart law. Biot-Savart law describes magnetic field produced by a current. Okay, so let me write it down. Right. BIOT. Yeah. Bio. Okay, so my V looks like R. Okay, let me change it. Savart law. And let me add for a current. Because again, book presents also Biot-Savart law for a charge, but I explained to you that recently I stopped discussing that because it's not completely true. So probably I will first draw the picture of a wire. Let's say we have some piece of wire. It doesn't have to be, okay, slightly, let me make it look a little bit better. Okay, piece of wire. It doesn't have to be straight. This law, yeah, you will see. It can be applied for any wire. It doesn't matter if it's a straight wire or bent or twisted, right? For any wire. No restrictions. Basically, it's sort of like a universal law, right? You can find any wire in the universe with current, and you can apply that to find magnetic field. So let's say you want to find magnetic field at this point P. Okay, it looks like D. It's Monday, right? I spent the whole weekend grading classical mechanics homework. All right, so let's assume that we want to find magnetic field created by this wire at this point. So what can be done? Of course, since the wire is not straight, each piece of this wire produces magnetic field in a slightly different, under slightly different conditions. So we need to treat each segment of this wire differently. So it means that we need to take infinitesimally small section of the current and write magnetic expressions for the magnetic field created by that section at this point. So I will take infinitesimally short ds. Yeah, I didn't show the current. Of course, there is a current over here flowing, right? So current. So if I take infinitesimally small section ds, which is at a distance r, okay, where should I write? At the distance r from the point in question, right? Then we will need to introduce the unit vector r hat. Can you see it's r? Okay, it's slightly tilted. Let me write it straight. R hat. Unit vector. Basically, what's the idea of that unit vector? Okay, so first of all, any unit vector has a magnitude of 1. So if you find absolute value of r hat, it will be just 1. And its goal just to show the direction to the point P. So point P is that way, okay, so r hat is that way. Point P there, that way, so point r hat points that way. P there, point r vector r hat is also that way. Right? Because so far, most of the time you used only I hat, j hat, k hat, right? Showing directions, positive direction of x, y, and z. But in this case, it just shows the direction to the point P. Right? So you'll have to get used to these ideas, right? Because they're used almost everywhere in science. Right, so as a result, after this, yeah, another thing. Direction of ds. You see, I wrote it as a vector. Direction of ds is determined by the direction of the current. Right? Okay, so let me write. Which way I should write? I'm just trying to word it. Okay, let me write. I defines a direction of ds. Right. And then, of course, again, about r hat, it's just basically vector r divided by magnitude of r, right? Of course, you can introduce vector r. And I will emphasize again that the absolute value of r hat is 1. Right. And so now, finally, the expression for the magnetic field. dB, on purpose I write dB because it will be a small contribution to the net magnetic field at this point from this section. Right. So it will be mu naught nu universal constant. Permeability of free space, I will write the value of mu naught in a second, divided by 4 pi. Okay, 4 pi you all know. Then the value of the current. Then cross product of ds, this ds, and r hat, this r hat, and divided it by r squared. That's the Biot-Savart law. Let me frame it. Again, it's a contribution to the net magnetic field at this point from this small section. Of course, if you want to find the net magnetic field created by this wire, of course, you will have to integrate from that side to all the way to that side, to that end of the wire, right? And then of course, you will get the net magnetic field at that point. Right? So now, mu naught, of course, mu naught, it's 4 pi times 10 to the power of minus 7 Tesla. We need to get rid of meters and also need to get rid of amps, right? So the units, Tesla times meters divided by amp. Let me check. Yeah. And it's called permeability. Permeability over free space. Idea, so the physical idea behind permeability is very similar to physical idea of epsilon naught. Epsilon naught, you remember, it sort of describes electrical properties of a vacuum. The same with mu naught. It describes more magnetic properties of a vacuum. Right? Of course, if that space is filled with some material, of course, this mu naught would be transformed to some mu, describing that particular material, magnetic properties of that particular material. So then, what else? Yeah, since we introduced magnetic field, units must be introduced. Magnetic field is very much more popular than the electric field. So, right. So, let me write here. So, units of B, T, which is Tesla, named after a great engineer, a researcher, right? Not named after the car. I hope you still remember that Tesla, it's the name of the person, not just the name of the car. All right. Just because of that it's basically the first associations now, when people hear Tesla, it's a car, not a person. That's why I don't like that car. Right? So what else? Yeah, it's enough of this expression. And the last piece, right? You know, maybe I will write it here. This can be applied for any piece of wire. Let's apply for an infinitely long straight wire. Most of the time we're going to use this, right? Of course, infinitely long with current. Okay, let me write something. So if we apply okay, this Biot-Savart law, I will just abbreviate BS law. Sorry, BS, it means Biot-Savart law. All right. And for an infinitely long, it's a sign of infinity. Sign of infinity, infinitely long. I'm just lazy to write infinitely long. Straight wire. With current I. When I started teaching this course, I think it was in summer 2014, I integrated Biot-Savart law to get the formula. And students were looking at me with round eyes, what are you, completely nuts, right? Because it was kind of tedious integration over like 15 minutes, right? And after that, I stopped going over that integration, right? I usually just write down the formula. Because this formula, in a class or so, we will derive easily using Ampere's law. Biot-Savart law using Biot-Savart law to get this formula is not that simple. So I will just write the, first let me draw the wire. So let's say this is our infinitely long wire with current I, right? And let's say we want to find a magnetic field at this point P, right? So at a distance r, perpendicular distance r, right? So r, it's a perpendicular distance in this particular formula. It's the shortest distance between the point in question and the wire, the shortest distance, the perpendicular distance, right? So in this case, B equals mu naught times the value of the current divided by 2 pi r. So this formula we will use a lot. Students usually don't have problems remembering this formula and using it so far. Now, it's the magnitude. What about a direction? First of all, if you have a wire, infinitely long straight wire, magnetic field lines form circles, sort of like this. So wire and the circle. Of course, the center of the circle is on the wire. Right. And so now if you remember that magnetic field lines form circles, then next question, what about direction? Direction, of course, you can use compass needle, right, as our probe system to find the direction, right? To find how God created nature this way. But of course, using compass needle every time is kind of tedious, right? And plus, not very often we have compasses right next to us. So as a result, we have right-hand rule number 2. So how we use that? How do we use the right-hand rule in this case? So let's say current direction that way. Just outstretch your thumb in the direction of the current, and then curl your fingers around the wire, around. So the wire is in your hand, right? So, and then direction of your fingers, direction of the magnetic field is given by the direction of your fingers. So right-hand rule number 2. Right-hand rule number 1 is used to find direction of the cross product. That's number 1. And this was, I usually call it number 2, right? So, and again, usually after a couple of examples, again, students don't have any troubles using this right-hand rule number 2. It's quite easy. Right, so let me draw magnetic field lines, maybe. Use So it will be a circle. Okay, I'm trying to draw a three-dimensional picture, right? So that's why there is no line over here. That line is behind the wire. So in this case, if I would stretch my thumb that way, so direction of the current will be this way. Wait, direction of the magnetic field. Direction of the magnetic field lines. And then, of course, I can draw even more these magnetic field lines. Right. Okay, let me write. So, and direction, right hand rule number 2. Okay. So that's what I was planning to review. And now let's solve a couple of problems. So 14a. Okay, let me separate this. 14 and problem A. There is a B and C, but B and C, that will be for your homework. Actually, A, B, and C will be for the homework. So what do we have here? 2 wires parallel to each other, infinitely long, this case. The simplest case. We'll usually start with the simplest, right? Parallel to each other, but directions of the current opposite. That's why I put the markers, you see. So this points that way, and this marker points that way. So 2 currents parallel to each other, 2 wires parallel to each other, but currents are opposite. Right? So we'll need to find the magnetic field at a certain point. Let me draw first the situation. Probably I will draw it here. Yeah. So blue will be the top wire. Right. Current this way, I. Right. And the lower one will be green. Right, so let's see. This is green. And the current, of course, is in the opposite direction. And also let me label this as wire number 1, and this is wire number 2. So then some distances are given. So the distance between these 2 wires is L. Then this is part A. In part A, we need to find magnetic field at this point. Which way I label it? Yeah, it's actually in the book, it's labeled point A. We need to find, in part A, we need to find magnetic field at point A. It makes sense, right? And the distance to that point is from the top wire. The distance is D. Okay, let me give you numbers. So I currents are 5. Okay, let me check 5 amps. No, 10. I don't know why I thought about 5. 10 amps. Then L, this distance between wires, are 2 centimeters. Then D is 4 centimeters. Don't forget to convert them over here. This must be in meters in order to get Teslas properly, right? Otherwise, your units will be screwed up completely, right? So here, you must use meters. And we will use it, of course. So let me convert over here immediately. 4 times 10 to the power of minus 2 meters. Right? Very common place for silly mistakes, really. Right? Not many students, but do. Some do. Right, so physics is quite simple, right, to discuss. This wire, infinitely long, straight, creates magnetic field from that infinity all the way to this infinity, right? So the whole space will be filled with the magnetic field produced by this wire. Then this wire creates its own green magnetic field, again, which fills the whole space. So at any point, this point, that point, any point you take, there will be superposition of 2 magnetic fields. So we asked to find the magnetic field at this particular point. In your homework in part B, you will find the magnetic field, the net magnetic field at this point, and then part C at that point. Very similar idea, right? Okay, so now I can write so B at point A, and again, let me emphasize, it's a net, right? B at point A, net, right? It will be, of course, B1, which is my blue, plus B2, which is magnetic field produced by the green wire, right? Okay, I want to write the final answer in a vector form. So let me introduce coordinate system. Right? Of course, you have constitutional freedom to introduce any coordinate system you want, right? Since I have also that freedom, so I will pick this way. So z-axis will be out of the board. Actually, let me remind you, in physics 1, we already used that. Let me remind, and of course, in the lecture tomorrow, I will remind you also. If you have this symbol, for example, for a vector, what does it mean? Circle with the dot in the middle. It basically means vector or current going towards us. Out, yeah. I see somebody answered out. Yeah, it's sort of like imagine an arrow flying towards you. So you will have a sharp edge, right? Sharp tip, right? And then the edge of the arrow. So this is out. And of course, if you have a cross, it means it's into the board or into the page. Again, it's sort of like an arrow flying away from you. If you do that, if you imagine, of course, you will see a stabilizers, right? Crossover stabilizers. So it's a into, right? So I can use it here. So I picked my z-axis out. So that's my z-axis. Because everything will be in the z direction, z is enough. But if you want, you can introduce also x and y directions, right? Not a big deal. So let's say this is x and this is y if you want. But again, we're not interested in x and y. Okay, so now as a result, let's show direction of the magnetic field, first blue and then green. Absolute values we know, it will be mu naught I divided by 2 pi and a proper r. Let me draw first a direction at point A. So what will be direction of the magnetic field produced by this blue wire? Direction, right-hand rule. So outstretch your thumb in the direction of the current, it's that way. And then curl your fingers, right? So curl your fingers. So above the wire, a magnetic field will be out of the board. Below the wire will be into the board. Imagine yourself, just grab a marker or pen, right, and you can see it, right? So above it will be out, blue, below in, right? So this is blue, so I will use blue color, right? So it will be, I said what? Out, right? Out. Out is dot. So that is B1, right? And of course, a B1 below will be here, cross. And here, B1 will be crosses, represented by the crosses below the wire. But above, out. So every time the magnetic field above in one direction, below in the opposite direction, because circles. Now let's do the same with green. Green, now outstretch your thumb. Direction of the magnetic field above will be into the board, so cross. And of course, below will be out, dot. So green over here, it will be, what did I say? In. In, cross, so it's a B2, but, and here also will be B2. And here will be out, B2. These parts will be useful for your homework. That's why I drew it. Right. Okay, but in our case, B1 is in the z direction positive, B2 is in the negative z direction. So as a result, I can write B1, it will be mu naught I divided by 2 pi. And what's the direction from the wire 1 to the point A, to the point in question, because that's the magnitude of the magnetic field, and R, you see R. R, it's a distance from the center of the wire to the point in question. In our case, this is the wire and the point in question A. So in our case, distance D, right? Distance D from the blue wire. So here I have to write D, and the direction is B1 is in the Z direction, so I can write plus Z hat. Plus, just emphasize that it's in the positive Z direction, right? Of course, you can use K hat. Not a big deal. You know that at this point that you can use a Z hat or K hat. Everyone will understand you. Then plus mu naught, now the green contribution. The absolute value of the currents are exactly the same, so that's why I don't use any subscripts next to the current. Then divided by 2 pi, and which distance now from the green wire to the point in question? Green wire here, point in question here, so we have L plus D. So that's the perpendicular distance, the shortest distance from the green wire to the point where we want to find magnetic field. So here it will be D plus L. And direction, of course, opposite direction of the magnetic field. Cross, it's a negative Z direction, so over here I will put minus Z hat. Okay, let me make this L shorter. Z hat minus Z hat. Okay, so now as a result, of course, we can factor out a few things, right? Mu naught I divided by 2 pi. I can take Z hat also outside, and inside I will be what? 1 over D minus 1 over D plus L. Okay, just cosmetic changes. Right? So you'll have to calculate less. And of course, don't forget to convert D and L into meters, right? So use 4 times 10 to the power of minus 2 and 2 times 10 to the power of minus 2. Mu naught is our universal constant, 4 pi times 10 to the power of minus 7, right? Of course, every time this constant will be given, right? So I'm not going to calculate this. We will just write down the, I will just write down the answer. It will be 6.7 times 10 to the power of minus 5. Direction Z. And obviously it's positive because contribution from the blue wire is going to be stronger than contribution to the net magnetic field from the green wire, because this is closer to the point where we want to find the magnetic field, right? So wire closer, of course, magnetic field is stronger. Wire is farther away, magnetic field, of course, weaker. So weaker contribution, stronger contribution, of course, as a result, this term is larger than this, and net magnetic field is going to be positive, right? So it's in Z direction and units of Tesla, of course. SI units of magnetic field, Tesla. Of course, if you use different systems, there are different units, Gausses, right? Okay, and of course, in words, of course, it will be out of the page, out of the page, or out of the board, right? But Z direction is shown, of course, it's enough. It's more than enough. All right, so this problem, the next one, we don't have enough time to discuss the next problem, right? As a result, let's just quickly refresh the cross product. I'm thinking about doing this. Or maybe I will discuss cross product probably in the lecture first, right? And then we will practice it here. Right? All right, so then I will start another problem, and then we will finish it next lecture. So in this example, 2 wires were parallel to each other and anti-parallel in terms of current direction. But now what if we turn one of the wires by 90 degrees? And now we have a system like this, you see? they're still kind of parallel and kind of perpendicular to each other, right? So not like this, now we have like that. So what will be the magnetic field at the center between the, so this is the shortest distance between these wires, the shortest distance, and we want to find the magnetic field in the middle of that distance. So I will erase this right quickly, and let's discuss that situation. Before I didn't discuss this problem, but once a couple of times I gave it on the exam, and I don't know, 50% of students bombed it. And I will explain where. As a result, I decided, okay, we need to discuss that in the class because we are not capable of extending what we discuss here to that particular situation. So this problem is not from the book, right? So what we have, let me draw it here probably. So the first wire, the top one, is, you know what, let me use also blue and green, right? Let's do that the same. So the top one was green, no, the top one was blue, let me use blue, right? So that's IT. T stands for top, the top wire, the upper one. Then, and it's out of the board, dot out, right? Then the green one is below, perpendicular, right? So that's IT and, no, IB. So current, B stands for bottom, B, right? And the top one is IT 20 amps, IB 12 amps. And as I said, we need to find the magnetic field at the center, right? So this is the center, so this distance is L, this distance is also L. So L is 10 centimeters. Again, don't forget to convert to meters immediately. I will convert it. So we need to find magnetic field at this point. So let's call it point P. So we need to find B at P. Again, physics is the same like in the previous example, right? So just configuration is of currents are different. So this creates magnetic field everywhere. This wire creates magnetic field everywhere. They infinitely long straight wires, so this formula can be used to find magnitude of the magnetic field. Direction, right-hand rule. So again, yeah, we will use that formula, right? So B equals mu naught I over 2 pi R. So let me frame it so it's sort of like a foundation. But the problem is in the picture. Let's draw the picture nicely because that's where students fail, right? Let's find direction. Direction of the magnetic field produced by the top one. Outstretch your thumb in the direction of the current and curl your fingers around. So as a result, we will have magnetic field lines, this circle, right? And of course, below, magnetic field will be that way, right? That way, right? You see. So magnetic field, I will use blue, will point this way. So that's B produced by T, top wire. Right? Now let's do the same for the low one. So again, outstretch your thumb in the direction of the current, and the magnetic field will be sort of above the green wire, will be out of the page. Out of the page, out it's a dot. Of course, below will be cross, because it will be in. So dot, so this will be B. Okay, let me hold you for a minute, right? So I just want to show the main point, because on the exam I asked, okay, guys, find the magnitude of the net magnetic field. And most of the students, took mu naught I divided by 2 pi L, mu naught IB divided by 2 pi L, and just added absolute values together. But it's not the case in this case, because you need to look carefully at the picture. Let me draw what we see from the top. Let me write top view. Top view. So here, imagine that your eye is over here. So what you're going to see? Green, B, B. It's towards us, but if you look from the top, it will be down. And B sub t, it's still that way. So, if you need to find the magnitude of the net field, so what do you have to do? First, you need to add them as vectors. That will be the net magnetic field, B net. And then if you need to find the magnitude of that B net, what do you have to do? Use Pythagorean theorem. BT squared plus BB squared, and take a square root of that. And not many students drew that, and as a result, they bombed the problem, right? So they just took the value of BT plus BB, and no, that will be correct if these vectors were parallel or anti-parallel to each other, like in the previous example. Now they're perpendicular to each other, right? It's once, of course, I drew that. Of course, everyone, oh, damn, it's so simple, right? Why I didn't draw it? Why I didn't draw it? Right? Okay, so now, of course, I can write, so B net will be square root of BB squared plus BT squared, right? And now the rest is trivial. You just take this, plug it here with the proper current. Again, take this second time and write it with the proper current, right? So you can, if you add them, you will end up with 4.66 times 10 to the power of minus 5 Tesla, right? Okay, I will send the solution, right, to you. But after drawing this picture, no one usually had any problems understanding the solution, right? Because that's why I keep telling guys, right, so draw nice pictures, because it simplifies understanding and reduces chances of making a mistake. Okay, guys, sorry for holding you, right, but I just wanted to get to this point, right? So if you have questions, ask. Otherwise, I'll see you tomorrow in the lecture.